Sahil, have you seen yesterday's lecture that we did? Were you able to go through it? Because most of the, okay, you are going through it. Chalo, theek hai. But most of the basic equations we have covered there. Of course, we have not done, I mean, we have, like cut short our derivations and other things just because that was not needed. Okay, theek hai. But convection, you could have gone earlier because today we were going to have convection session, okay? So radiation, you could have, done it later on. But chalo, theek hai. Now, what we are going to do today is internal flows. Okay, nice. Chalo, theek hai. So today's internal flows and free convection. Boiling and condensation, I have checked. Neither we got any questions in GATE. And boiling and condensation, I don't think it is in GATE. It is in ESC. So that's why I used to do it earlier. But still, if you are interested in learning about that, then you can, if you want, you can send me a personal message on my number. I can share the PPTs that I had made that I usually cover in class. Okay, so you can just read it out. You can just, it's very simple. It's not, there are 3-4, parts of boiling and condensation. Boiling has actually, it is divided into 4 regions. So you can have a good read over it and you can understand most of the part of it. So it is internal heat transfer, internal flows, okay, convection in internal flows, and then free convection, and then we will go to the questions. Okay, chalo. So we all know what is internal flow we have discussed, in which basically it is covered by a boundary. Okay, fluid is flowing through a boundary. Okay, it can be circular pipes, non-circular or rectangular pipes, or which is actually called ducts. Non-circular pipes are called ducts. We can have rectangular or square ducts. Rectangular or square ducts. Okay. So circular cross section can withstand large pressure. That's why we usually use it to transporting fluid. Okay. Can withstand large pressure differences between the inside and outside without undergoing significant distortion. That is why most significantly we see circular pipes. Only in air conditioning, mostly we use rectangular ducts and all. Okay. Chalo. Now, so let us talk about, like yesterday we draw hydrodynamic profile, du by dy, and temperature profile dt by dy for external flows. Let me check if other people have joined. Okay, Sean has joined. Very nice. Chalo, theek hai. Okay. So just one second. Okay. So today we are going to talk about internal flows. Now we all know that on the solid surface, whenever fluid comes in contact with a solid body, we have a no slip condition where velocity becomes zero. So same thing is going to be happening here. But now earlier we had only one boundary, okay, only one surface. Now it is covered by surface, okay. So let us take a pipe. Okay, this is a pipe. And again, as we take two coordinates, let us take coordinates, okay, x and y. At this point, we are taking x and y is in vertical direction going up, x is in horizontal direction going in the forward direction, okay. And r at the center, r is equals to 0, and it is increasing. So here, r is equals to capital R or R naught. Okay, chalo. Now a fluid is flowing, air, water, whatever, with a uniform velocity u infinity. It is the free stream velocity we talked about yesterday, u infinity. So it is unaffected by the viscosity, and it is not affected by the viscosity. So it is uniformly distributed velocity. Now, we all know what is going to happen. This fluid, as soon as it will enter into the pipe, here at this point, what will happen? Can you tell me what will happen at this point? The layer that is in contact with this, Yes, here u will be equal to 0. Also tell me what will happen here. Here also, yes, u will be equal to 0. Now the velocity. Earlier the velocity was varying from u is equals to 0 to u is equals to infinity. But this time, what will happen? The velocity is going to vary from 0 to 0. It will going to vary from, okay, from 0 at one boundary to 0 at another boundary. Okay. Now, of course, velocity will be 0 here. Of course, velocity will be 0 here. But as soon as it will go a little down, velocity is going to increase a little bit. Then it is further going to increase a little bit. Then again, it will going to increase a little bit more. Now, somewhere here, it will be equal to maximum velocity, like this. And it will be reducing here and here also little bit. So the profile that will be formed here is like this. Now we have reached maximum. So it will be like this and this. Okay. Now it is going to grow. It is going to, now here you see here, if we talk about this, u is varying in r direction, isn't it? By it is varying in the radial direction. It is varying in r direction. It is also varying in x direction. It is also varying in x direction. Okay. So you see here, it is varying in x direction. How it is varying in x direction, you see. Let me draw one more diagram. So again, here it will be 0, here it will be 0. Okay. And now the gradient is going to change. How it is going to change? Now at third point, it became same as the maximum velocity, but this time it is going to further extend and again, and now it is same. This is because of the viscous forces. Okay, now this much and this much. So now it increased like this, then it became equal to maximum velocity, and then, so now you see, when we are going in x direction, it is varying also in x direction. Okay, x direction velocity is changing, right? Here we are saying in r direction, but if we compare this and this, we can see that velocity is also changing in x direction. Now after a certain point, when we reach here, when there's a word that we say, but after a certain point, once we reach here, let's say here, so what will happen? It is going to increase, 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 and there it will become maximum. Then it will reduce, it will reduce, it will. So it is parabolic. Now this is parabolic. Okay. Now where you reach this point, it is called as fully developed flow. Now this is now it is only a function of r. Now if you go ahead in this direction, one second, I'm sorry. If you go ahead in this direction, your velocity profile is going to remain same. It is not going to change in x direction. It is not going to change in x direction. So after this point, it is called as fully developed flow. It is developed flow. And there it is, flow is developing, is still developing. It is called as entrance region, developing flow. After once you have reached at the point that fluid is completely developed, then the fluid is not, then the u is not going to change in x direction. It is only going to change in, now whatever diagram I draw here, it will be exactly like this. But you see here the gradient is increasing like this, and then this is changing. Okay, so let me show this to u. So I am rubbing this because I have already made an animated diagram. Okay, so I am rubbing this, right? Chalo. I just wanted to explain you this before I show you the diagram. Now what is happening here? Now let's see what is happening here. Here r is equals to 0. Here r is equals to r. Chalo. So this is your first profile. As soon as it is entering, it is like this. First of all, it is increasing linearly, and then this is the gradient. So here u is a function of r and x. If you further go ahead, then the profile will become slightly more parabolic. It is going towards parabolic. Okay, you go further, then it is completely parabolic. So this point, if we divide this point here, so what we can say now, and you see here at this point it has reached u is equals to 99% of your u max. If at the center you have u max, then at this point you have reached, in fact, yeah, at this point you have reached 99% of u max. Now this is going to increase. Here also you have reached 99% of u max, but when you reach, now this time you have reached here 99%. After that it is not going to change. After that it is not going to change. So this is called as your boundary layer. This is called as your hydrodynamic boundary layer, and this is your thickness. This is your hydrodynamic boundary layer. It keeps varying. You see here it is this. As you are going from entrance region to the fully developed region, your hydrodynamic boundary layer thickness is increasing. Okay, now after this point it does not increase. Now here it will remain as this only. Okay, so this is hydrodynamic boundary layer thickness, right? Now so this is your inviscid region, this side, and this is your boundary layer region. This is your boundary layer region. Okay, here you can feel the stresses. Viscous stresses are dominant here. Okay, now this is called as hydrodynamic entrance region, and this is called as fully developed region. Now after this the flow is fully developed, the profile is going to remain same, and it is not going to change. It is not going to change. Okay, so these kind of profiles are formed in a internal flows. Okay, chalo. So what is hydrodynamic entrance region? It is the region from the pipe inlet from x is equals to 0 to the, at the inlet x is equals to 0 to the point at which the velocity profile is fully developed is called as hydrodynamic entrance region. So this whole region from here to here, it is hydrodynamic entrance region, and the length of this region is called as hydrodynamic entry length. So this is LH. Okay, the hydrodynamic entry length is usually taken as the distance from the tube entrance where the wall shear stress reaches within about 2% of the fully developed value. Okay, so your wall shear stress keeps on reducing and reaches to 2% of the fully developed region. Now these are some given values for hydrodynamic entry length for laminar and turbulent flow. Okay, so these are experimentally defined. 0.05 Reynolds number into characteristic dimension. Okay, for turbulent it is much higher, 10D. Turbulent means if turbulent flow is there, then it is much higher. Okay, it will be much higher. Okay, chalo. Now the problem with internal flows is something that, like we had a constant velocity in external flows. You see, once we have reached this point, we can say that you can take a reference of your free stream velocity u infinity. But in internal flows, it never reaches to your u infinity. Okay, it keeps changing. You see, it keeps changing, and it is reaching, let's say, v max, but it is still not u infinity. It is something different from u infinity. So there is no criteria of u infinity in internal flow. It never reaches u infinity. Okay, it depends on the characteristic dimension of the pipe. Okay, so what is the maximum velocity? But it never reaches the u infinity value. So therefore, we cannot use u infinity. In there, whenever we were calculating Reynolds number, we took, what did we took? Rho u infinity characteristic dimension by u. So this was a reference velocity to calculate dimensional parameters and other calculations as well. Okay, but here we do not have any concept of u infinity. So we have to define the average velocity. What do you mean by average velocity? By here velocity is equals to 0. Here u or v, whatever it is, let's say it is 0. Then it is slowly increasing. It reaches v max at the center and then again starts reducing. At this point, by it is reducing here and then it is reducing here. Okay, here also v is decreasing. Here also v is decreasing. At r is equals to 0, we have reached v is equals to v max. Okay, so it is continuously changing. It is continuously changing in the pipe. So we do not have any reference value to take, and therefore we need to make a calculation for average velocity. We need to calculate average velocity. Now axial flows, the free stream velocity served as a convenient reference velocity for use in the evaluation of Reynolds number and the friction coefficient as well. In internal flows, there is no such free stream, thus we need an alternative. What is the alternative? By fluid is changing from 0 to the surface and because of the no slip condition to a maximum of tube center. I have already told you all this. It is just written here. Okay. Therefore, we need to define a V average that will remain constant. Average velocity. Okay. Now, how do you do that average velocity? How do you calculate your average velocity? Okay. So you see, whenever a fluid is flowing, of course, there will be mass continuity equation will be valid. All three equations, all three conservation equations. What are three conservation equations? Continuity or mass conservation, momentum conservation, and energy conservation. So by using our mass conservation equation, we can define our V average. How do we define V average? By here in this area, you see, if I take this profile in this area, there is velocity is continuously varying in radial direction. All the analysis are done in fully developed region. Okay, in developing region we do not do any analysis, and anyway that is very short. If you have this pipe, so very small region is entrance region. After that it is always fully developed region. So all the analysis are done for fully developed region, not entrance region. Okay, now that's why we are only taking u is a function of r. Okay, chalo, 1 second. So you see in this area there is some mass. If I draw this profile, there is some mass here. Okay, some mass is there. If I take a similar mass in this area, if I take a similar mass, but now my velocity is average velocity. Now in this particular area, the velocity of the fluid is V average. How do I know it is V average? Because I'm going to equate the masses. I'm going to equate the masses by mass in this blue region. Mass flow rate in this blue region is equals to mass flow rate in this red region. In the red region, my velocity is continuously changing in r direction. It is continuously changing in r direction. But in my blue region, it is not changing. I have taken some average velocity, but it is compensating for the same mass as in the red region. Okay, so I have done by mass conservation for blue and red region. So for blue region, It is rho AC into V average. And in blue region, by it is changing. So I have to do what? I have to integrate it from 0 to capital R, 0 to capital R. Okay. So from here, let me take V average is equals to rho UR DAC upon rho into AC, rho into AC. Now what can I write? By abhi to I am talking about area, but I can express area in form of radius. So what can I do? Rho UR 2 pi R. It is a very small R I have taken. dr. By what very small R I have taken? At any point I have taken a very small R. A small element I have taken. Okay. So now divided by, now this is cross sectional area. So it is rho into pi capital R square, because I am only talking about this mass. Okay. So I can take my whole radius. Okay, pi by 4 d square you can say. This is my cross sectional area. Okay, chalo. Now I can cancel few things. By density is constant, property of fluid, density is constant, pi can be removed. Okay, ठीक है. Now what am I left with? By 2 comes out, r square comes out, 0 to r, now it is changing. By r is equals to 0 at the center, r is equals to capital R at the boundary. R UR R dr. This is my average velocity. Now I have to integrate it so that I can calculate my V average. Okay, so this is my definition of V average. I have defined my V average. Now it will serve as a reference velocity for my calculations. If I calculate Reynolds number, I will take V average, not U infinity or something. Okay, there is no concept of U infinity in internal flows. Okay, chalo. Now we will do the same thing. Do you remember what did we do there in our external flows? How did we define the velocity profile? We solved our continuity equation and we solved our momentum equation. We solved two equations and we defined a profile. Okay, similar thing we are going to do here. Okay, so we will get a velocity profile like this, and it has two constant. Now I need to calculate C1 and C2, so I need few boundary conditions. What are the boundary conditions? By I know one thing, what? At R is equals to 0, V is equals to V max. So यहाँ पे dV by dr will be equal to 0. Here it is not changing in respect to with respect to R direction. Is it okay? Okay. Can I also say at R is equals to capital R, U is equals to, yeah, V is equals to 0. I can say this as well. So I have two boundary conditions. I have two variables C1 and C2 to calculate. Okay. So I can put my boundary conditions in this equation. And if I solve that, then I will find that this is how my U is varying with respect to R. This is how my U is varying with respect to R. Okay. Now my purpose, there also my purpose was to calculate how du was changing in y direction. Here my purpose was to calculate how du is changing in r direction. So this is my equation. It is telling me u is a function of r, and how it is related to r? By this relationship. Okay. Now I need to calculate V average. And I have already defined the definition of V average. Okay. So now I need to substitute this UR in this here, and then I have to integrate. Okay. Therefore, the velocity profile in fully developed laminar flow in a tube is parabolic. with the maximum at the center line and the minimum at the tube wall. Okay, you can put your boundary condition, and you can also find that when you put r is equals to 0, it will be equal to del u by del r will be equal to 0. If you put r here, capital R in this equation, then you will get ur is equals to 0. Okay, it is going to satisfy your condition, boundary conditions. So now I need to substitute ur here, and then I need to integrate this. Once I do that, okay, so this is what I have done here. This is my velocity profile, u as a function of r, and this is my definition of v average. Now I am going to substitute this here, and when I am going to integrate this, I will find v average is equals to minus r square by 8 mu dp by dx. Okay, dp by dx. Chalo. Now I can substitute this. Here by it is related to this. I can substitute this. So what will I get? I'll get ur as a function of v average, because usually v average will be given you in question. Okay, so I need to define everything in terms of v average. So ur is related to v average using this equation, and if I substitute r is equals to 0, why? By r is equals to 0 gives me v max. So if I put 0 here, it will be equal to 2v average. 2v average. Okay, because if I put 0 here, then it will be just 2v average. So v max is equals to 2v average. If I substitute r is equals to 0 and ur as v max, I will find v max is equals to. So three things I have found. What? How u is changing with respect to r. Then what is the value of v average, and what is the value of v max. These three things are important here. Although very few times internal flow problems comes, but anyway, chalo. Now let's move on. Chalo. Now also we need to calculate pressure drop. It is basically your fluid mechanics problem. Okay, we all do this in there, but the thermal boundary layer we only see in HMT. So there also we have done it, how the pressure is changing in x direction. Okay, so dp by dx, I can say dp p2 by p1 by l, my x2 minus x1, and x1 is equals to 0, so only I have l. Okay, what is the pressure drop if this is my pipe? So what is the pressure drop from x is equals to 0 to x is equals to l? That I need to find out. So I have defined my v average like this. This is my v average. Okay, from here let me take out dp. So dp, and if I take minus here, so by dp is equals to p2 minus p1, but minus dp will be p1 minus p2. So I can calculate p1 minus p2 v average, and dx is equals to l. Dx is equals to x2 minus x1. This is x1, this is x2. So dx is equals to x2 minus x1. This is l minus 0, it equals to l. Okay, so I can just put it here, and I can calculate my p1 minus p2 as 8 mu lv average by r square. And if I replace r by d, then I think I'll get 32 mu lv average by d square. I'm hoping you have seen this in fluid mechanics, this formula. Okay, ठीक है, चलो. Now, pressure loss can also be given in terms of Darcy friction factor. And I know that you also study friction factor and friction coefficient in fluid mechanics. Okay, the same formula is here and the same formula is there. Okay, so it is also expressed in terms of F LD by rho V square average by 2, where rho V square by 2 is dynamic pressure and F is the Darcy friction factor. And it is also defined Darcy friction factor as 64 mu rho dV average, and it is 64 upon Reynolds number. Also, this formula is familiar for us. F here is friction factor. F here is friction factor. Okay. We can also express this in terms of friction coefficient. Can you tell me? Do you know the relationship between friction factor and friction coefficient? Waiting for you. This is F is friction factor, CD into 2, coefficient into 2. There is also one more relation that is between friction factor and friction coefficient. That's what I am asking. Friction factor and friction coefficient. So friction factor is equals to 4 times of friction coefficient. Sometimes they will give you friction coefficient. Yes, 4F. That is right. Sometimes they will give you friction coefficient. So first we will calculate friction factor. Okay. And then you can calculate the Reynolds number from there. Okay. So this equation shows that in laminar flow, the friction factor is a function of Reynolds number only and is independent of the roughness of the pipe surface. Okay. This is about laminar flow. In turbulent flow, it is a function of both Reynolds number and roughness. Okay. Now head loss is given by delta PL by rho G. So head loss I can calculate using this formula. By delta PL will come from here. And I can cancel my rho and I will get this. Okay. So I hope these formula are at least you are familiar with all these formulas, because whenever we discuss about boundary layer, hydrodynamic boundary layer in fluid, we discuss all these formulas. Okay. Chalo. Now next is our thermal boundary layer for internal flows. So same thing. Now it is not animated. It's simple diagram. Last one was animated because I wanted to show you. Okay. So it is also same. Look, what is same? By you have this pipe and you have this fluid that is at T infinity. That is at T infinity. Okay. Now as soon as it will enter, it will take, if it is wall temperature. Let's say wall or surface temperature, as I told you earlier. Sometimes you say wall temperature, sometimes you say surface temperature. In question, hello. So dW or DS, whatever. Sometimes in question, in exam, they say TW or TS, surface temperature or wall temperature. Okay. Now at the surface here at this point, the fluid temperature, that T, will be equal to how much? And I am saying my condition is what? T wall is less than T infinity. That's how we are doing heating of fluid. Okay. So fluid is taking heat from the wall. Your pipe is maintained at a higher temperature. Okay. So can you tell me what is the temperature at the surface? What is the temperature at the surface? Yes, it will be equal to TW. Wall, whatever the wall temperature. Of course, it will be slightly less, but we can assume it is TW. Okay. Now, as you are going in R direction, as you are coming here, your temperature is going to reduce. It will be reducing from TW, which is the highest temperature in the pipe, to T infinity. But of course, it is not going to go to infinity because this wall is also maintained at TW. This wall is also maintained at TW. This surface is also at TW. So it is going to reduce. It will reach to a minimum temperature somewhere here. By at R is equals to 0, your T is equals to T minimum. T minimum. Okay, so first of all, it is going to vary like this. Here, at this point, you will get T is equals to 99% of your T minimum. And same here, same here, same here, same here. Okay, so I'll take this point, and then it is going to further decrease, and it is going to, so now at this point, you have T is equals to 99% of T max, T minimum, I'm sorry. Okay, so I'll mark this point. Similarly, this side I can mark this points, and then finally, this profile will be changing, and only T minimum will be obtained here at this, at the center, and this is will be, and after this, if you are going in this direction, your temperature profile will remain same. Okay, so at R is equals to 0, T is equals to T minimum. At R is equals to capital R, T is equals to TW. Okay, this is how it is changing. Now this is your, of course, viscous region. Here stresses are dominant, shear stresses, viscous region, and temperature gradients are present. Okay. Now again you can see here that in this region, temperature is a function of what? Temperature is a function of what? R as well as X. Yes. But in this region, temperature is not changing with X. It is only a function of R. Okay. So again, it is called as thermal entrance region. The left side is called as thermal entrance region. The other side is called as fully developed region. Okay. And this is called as your thermal boundary layer. It keeps changing until it is fully developed. So once it is fully developed, then fully developed region starts. Okay, then the whole area, this is your thermal boundary thickness. Okay, so this is your heating. What happens in cooling? By cooling, if this is your wall temperature and this is your T infinity, now T infinity is greater than T wall. So we have maintained our pipe boundary or duct boundary at lower temperature. So what will happen? If fluid is going to get cooler, as soon as it will come in contact with the boundary, it will going to give some heat to the boundary, and that heat will be gone out. Okay, so now it is the cooling of fluid. Now fluid is getting cold. Now same thing will happen here. At this point, T is equals to T wall, which is lower temperature. At the center, you will have maximum temperature. Okay. So slowly, as you are coming down, your temperature is increasing. It will going to get to the maximum temperature, and then it will start reducing. Because also here we have T is equals to TW. Okay, so here in this region, it is the thermal entrance region. Also, you see when we draw our hydrodynamic layer, when we draw our hydrodynamic layer, you see here how was the profile. This is the profile. Here U is equals to 0. Here U is equals to 0, right? But here T is equals to not 0. Here T is equals to not 0, it is equals to TW. So it does not start at the same point. First of all, you have to show a finite temperature at both sides, because it is T is equals to TW. And then your parabolic profile starts for cooling of fluid. Okay, so there we were starting from this was your U as a function of R, but this is your temperature as a function of R. It does not start from the point. There is some finite temperature first, and then your parabolic profile starts. So you see here, I have shown what? This is little bit temperature here, which is equals to TW, and then your profile is starting. Now it will remain same. Now wherever you go further, now it is not going to change in X direction. It will be like this only. It will be like this only. Okay. So this is your fully developed region after this point. Okay. And this is your thermal boundary layer. Okay. And here also, this is your thermal boundary layer. Okay. Chalo. Is it okay? Should we move on? Now, this is the case of cooling of pipe. So you need to understand that the profile are different. It is heating of pipe. And this is cooling of pipe. So it is somewhat similar to the hydrodynamic boundary layer. Okay, but not exactly same. Okay. Chalo. Should we move on? चलो ठीक है. Now thermal entrance region and entrance length. Again, we know that what is the thermal entrance region. But till our temperature is changing with respect to, by here, my temperature is changing with R and X. But once it is not changing in X direction, then we called as fully developed thermal region. And the length here is called as thermal entry length. Okay. So thermal entry length, the region of flow over which the thermal boundary layer develops and reaches the tube center is called as the thermal entrance region, and the length of this region is called as thermal entry length. How do you give it? By it is equals to 0.05 Prandtl number, Reynolds number, and characteristic dimension. Do you remember hydrodynamic hydrodynamic entry length? What was it? 0.05 Reynolds number into D. Yes, RE into D. Okay. So this is equals to, now this is equals to Prandtl number into LH laminar. Okay, so maybe they will give you this, and sometimes you need to calculate this to solve further. Okay, and turbulent it remains same, 10D. In turbulent flow it remains same. ठीक है, चलो. Now again the same problem. One second. Again the same problem arises. What is the problem? By there we had a reference temperature T infinity. But now we do not have this reference temperature because it is not even allowing it. If it is reducing, reaches to a minimum, which we are not sure if it is equals to T infinity, but then it again starts increasing. Okay, it never reaches to T infinity. So again, we do not have a reference temperature. What do? We need to define a mean temperature or bulk temperature. Sometimes we say bulk temperature, sometimes we say mean temperature. Okay. Now, when a fluid is heated or cold, as it flows through the tube, the temperature of the fluid at any cross section from TS surface. So here it is TS, and it is decreasing, it reaches as T minimum. Here it is T is equals to TS. Then it is decreasing, reaches to T minimum. And then again starts increasing and reaches to T is equals to TS. In case of cooling, it's opposite. Okay, it starts from TS, increases, reaches to T max, and then again TS. Okay, so it changes from TS at the surface of the wall to some maximum or minimum in the case of heating at the tube center. Okay, so at R is equals to 0, T is equals to T max or T min, R is equals to capital R, T is equals to T wall at T surface. So in fluid flow, it is convenient to work with the average or mean temperature, which remains constant at a cross section. So we need to define our mean temperature, average or mean temperature. How do we do that? By, if I need to come up with a temperature that is mean temperature, I need to do a, what I need to do? Can you tell me? I need to do a energy balance. Yes, I need to do a energy balance. Energy balance. How do I do that energy balance? By energy in this area, in this blue area where temperature is varying, but it has some mass and its temperature is changing, so it will have some energy. Okay, but the temperature is changing with respect to R, so energy is also changing with respect to R. But the amount of energy, I will consider a different area, this area, and the amount of energy is same. Amount of energy is same, but here I have T mean. Here I have taken a constant temperature T mean like this. Okay, constant temperature T mean. So energy will remain same in blue and red area. But in red area, temperature is T mean. In blue area, temperature is changing with respect to R. ठीक है चलो. So I will do what? This is your red area. This is your blue area. Okay. Now it is what? It is rho Cp, because mass flow rate is what? Mass flow rate is what? Rho A V. Now I am going to take a certain area. I'm going to take a certain area in R direction. Okay, let me take one certain area in R direction. So it is rho dA cross section, a small area, and V is changing with respect to R. I mean, my velocity is also changing with respect to R in this region. Okay, for blue area. So I can write this rho ACUR, and CPTR is already there. CPTR is already there. So by equating this and this, I can calculate T mean is equals to rho Cp TR UR dA cross sectional area by M Cp Tm. Okay. Now I can also write this. I can also write this m dot in the form of my V average, right? So it is rho V average, rho AV. Area is A. Okay. So it is rho CPTR. One second. Rho CPTR UR. Now what is this area? Same. 2 pi R small area dr. Now what is this area? V average pi by 4 d square, या pi R square CP TM. Rho and rho can get cancelled. CP can get cancelled. Pi can get cancelled. And I will get 2 V average by R square. Now it is changing from 0 to R. TR UR R dr. Okay, this R is still there. TR UR R dr. ठीक है. So this is my definition of mean temperature. Now, I already have this. What do I have? I already have this. U, how U is changing in this, I already have. Okay. Now I need how temperature is changing in R direction. How temperature is changing in R direction. Then I can put that into this equation and I can calculate my T mean. Okay. Chalo. So temperature profile, again we will do the same. What we will do, we will solve our continuity. This time I need to solve all of them: momentum and energy equation, and I can define my temperature equation. How my temperature is changing with respect to R. But again, we have C1 and C2 as constant. I need two boundary conditions. To calculate this TR. So again, we know that at R is equals to 0, at R is equals to 0, T will be equal to T minimum. So del T by del R is equals to 0. Either minimum or maximum. Boundary condition will remain same. For cooling and heating, it does not matter, okay? And at R is equals to R, T is equals to T wall or T surface, whatever it is. Okay? So I can apply these conditions in this equation, and this is my temperature profile. How my temperature is varying with R. UR I have already calculated earlier when I solved my equations. So now it is time that I put TR here and UR here, and RDR is already there, and solve it. Okay, solve it. So this is what I get. TM is equals to TS minus 11 by 24 Q dot S capital R by K of fluid. Okay, ठीक है. So this is my mean temperature. This much is clear or not? Chalo. So let's move on. Now there are two cases here. Constant heat flux at the surface. That means you are providing QS, constant heat flux. Okay, Q dot S constant. This is basically watt per meter square. You are providing constant heat flux at the surface. This will remain constant. Okay, chalo. So if you are, and I already know that heat transfer coefficient will remain constant. It will not change. Okay, once I have decided my diameter of pipe, my characteristic dimension, the velocity, then it is not going to change. Okay, chalo. So how I can give Q dot S is equals to H TS minus T mean. TS minus T mean. Okay, chalo. Now look, I am saying this is constant, and H always remains constant. So in order to satisfy this condition, my delta T, which is TS is equals to T minus TM, it should also remain constant. So the temperature difference between surface and mean temperature will also remain constant. So I am not saying that mean temperature will remain constant or surface temperature will remain constant. I am saying the temperature difference must remain constant. Okay, how will it remain constant? Look, you are giving heat. Of course, your T mean is going to increase. But together, surface temperature is going to increase. But they both will increase in such a way that delta T will remain same. Only then it will satisfy this condition. Constant heat flux at the surface. So again, we are talking about fully developed region, not entrance region. Okay, in the fully developed region, first of all, it is going to increase. Okay, it is going to increase. It is the entrance region. Like this is my entrance region. It is going to increase. But then after that, the temperature difference will remain same. T mean will increase. Of course, look, we are giving heat. So this heat will be absorbed by the fluid. So of course, the temperature of fluid is going to increase. So surface temperature is going to increase, and mean temperature is also going to increase. But the temperature difference will remain same. This is your TI, this is your exit temperature. Okay, and the Nusselt number for this particular case is given by 4.36. It remains constant. It remains because H remains constant, D remains constant, K also remains constant. So it is 4.36. Okay. Chalo. There are one more case in constant temperature at the surface. Okay. Now I am giving heat. Look, what I am doing is I need to maintain constant surface temperature here, here, and here. So surface temperature line will remain same like this. Okay. Now Q dot is equals to H T surface minus T infinity watt per meter square. Okay. This is also watt per meter square. Now surface temperature will remain constant. Look, this will remain constant. It is always constant. And I am saying this condition must satisfy. This should remain constant. But you are giving heat. It is the heating case. Okay. So you are giving heat, of course. Q you are giving. Okay. So if Q you are giving, so I'm sorry, this is T mean, not T infinity. There is no T infinity here. T mean. So if you are giving heat in such a way that surface temperature will not change, but the heat is going inside and it is absorbed by the fluid. So the mean temperature of fluid is going to increase. So you see mean temperature of fluid is going to increase. It is increasing. And therefore, this whole temperature difference, Ts minus T mean, is going to decrease. You see, this is also decreasing. As you are going in X direction, temperature difference is going to decrease. And if this is going to decrease, your rate of heat transfer is also going to decrease. Okay, rate of heat transfer is also going to decrease. By temperature difference is decreasing, and you need to maintain Ts. So you have to give the rate of heat transfer will be low and low as you go forward. You have to keep decreasing it if you maintain this temperature, because as you are going in this direction, you need to keep your Ts constant. And you are adding heat to the fluid, but your fluid is getting heated, so T mean is increasing. Okay, so it will try to increase this Ts as well, but you need to decrease the heat transfer to keep that constant. Okay, so this is your case. So in this constant this is the graph. So they can ask the graph as well, or you have to remember that Nusselt number is again constant. It is not a function of other parameters. Okay, it is 3.66. H is constant, H always remains constant, D and K are constant. It is equals to 3.66. Okay, this much is okay. Yes or no? Chalo. Any doubt till now? Chalo. So this is kind of the summary of what we have done today. Again, internal flows, Reynolds number will be less than 2000. Turbulent flow, what is the Reynolds number? Can you tell me for turbulent flow in internal flows? Reynolds number is for turbulent flows, yes, greater than 4000. And in between it is transition flow. Okay, transition from laminar to turbulent. Okay, so first of all, we have solved our continuity and momentum equation, and we have defined our velocity profile. The purpose was to define average velocity. So I have calculated by average velocity also like this. Maximum velocity is equals to 2 times of 1 second. Okay, 2 times of V average, and we know pressure drop can be calculated according to this, and also in terms of friction factor, and where Darcy friction factor is 64 upon Reynolds number. Head loss is given by this formula. Okay, then we came to thermal boundary layer. Okay, so this was my temperature profile. An average temperature I can calculate by using TR, which is this one, and UR, which is this one, and we have to integrate it from 0 to R. So this is my mean temperature. More importantly, Nusselt number remains constant in this case. So for constant heat flux, it is 4.36, and for constant temperature at the surface, actually constant surface temperature case, it is equals to 3.66. 3.66. Okay. So this is kind of summary for your internal flows. External flows I have given you yesterday. Okay. So this is kind of, covers most of the things. I would not say 100%, because when you skip things, of course, there will be things that will be missed. Okay. But this covers actually 99% of what we need to cover. Okay, chalo. Now let us come to the next topic of free convection. Free convection. So we all know free convection takes place because of what forces? Because of what forces? Free convection takes place because of buoyancy forces. Yes. Okay, density difference. Whenever temperature is increased, the density of the fluid decreases and it starts moving upward or even downward if it is cool down. Okay, its density decreases, its density increases, and it starts moving downward. Okay. Chalo. If, for example, this is a cold plate, so fluid will come like this. It will take it, it will move down because its density is going to decreased. I'm sorry, increased. If this is the if this is the cold plate, if this is a cold plate, so T surface is less than T infinity. So fluid is going to come and give some heat, becomes colder, and its temperature P upon density is equals to RT. Temperature reduces, density increases. Okay, so density increases, it will start moving downward. But basically, it is the density change that is arising, that is causing the fluid to move. We are not using any external source, fan, blower, pump, or anything to move the fluid. It is only buoyancy forces, density that are caused because of the density difference. Okay. Now, net force that is acting is basically weight of the body minus buoyancy forces. So weight of body is what? Rho of body, G, and volume of body. And what is buoyancy forces? By rho of fluid, G, and volume of body. By volume of body, it is basically the whatever the amount of fluid that is replaced by the volume of the body is causing the buoyancy forces. Okay. So rho body minus rho fluid, G into volume of body, where rho fluid is the average density of the fluid and not the body. Okay, so this is of the fluid, this is of the body, and V is the volume of portion of the body that is immersed in the fluid. Whatever is immersed in the fluid is that volume we are going to consider, not all. If it is completely immersed, then we will take the total volume. Okay, chalo. Now here we defined T infinity, or we defined T mean. Here also we need to define mean film temperature. Mean film temperature. So so how this is moving. Look, there is a temperature that will. There will be a temperature that will be in this region. Okay, in this region there will be a separate temperature. It will not be T surface, it will not be T infinity. That is your mean film temperature. Okay, so here at the surface you have Ts, outside it is T infinity, but the fluid is coming in this area, the fluid is coming in this area and taking away heat, and it is moving, taking away heat and it's moving. So the temperature here is mean film temperature. How do you calculate this? It is the arithmetic mean of the surface temperature of the solid, whatever the surface temperature of the solid, and the undisturbed temperature of the fluid which flows over the surface. Okay, so it's the arithmetic mean only. Tf is equals to Ts plus T infinity upon 2. Delta T is Ts minus T infinity. Ts is surface temperature. T infinity is surrounding temperature. Now, here are some dimensionless numbers. Grosshoff's number we have already seen. Grosshoff's number we have already seen there. And there are few other numbers that are responsible in free convection. So the most dominant number is Grosshoff's number. Okay. So the flow regime in forced convection is governed by the dimensionless Reynolds number, which basically tells you the ratio of inertial to viscous forces. And it actually tells you if the flow is laminar or turbulent. Now, in the natural or free convection, the flow regime is governed by dimensionless number, Grosshoff's number. Okay. So yesterday we have, I think, did we do the derivation for it? I think we did derivation, right? Reynolds number into buoyancy forces and viscous forces. So we did derivation and we defined this, right? We defined this. So इसमें delta T is surface minus T infinity, temperature difference. And beta is isobaric volume expansion coefficient. It is basically beta is equals to 1 upon V, how the volume is changing with respect to temperature at constant pressure. So it is isobaric volumetric expansion. How the volume is changing with the temperature at constant pressure. So, for example, if temperature is increasing, there is a body. This is a body that is dipped in water. Okay, this is water and this is your body at higher temperature. So if its temperature is going to increase, its volume is going to increase, expansion will happen, right? Molecules will gain some energy, will try to push one another. Okay, so its volume may increase, and if volume is increasing, then buoyancy forces again will increase, because the volume of body, you see, the volume of body is going to increase. So it is going to affect the buoyancy forces. It is going to affect the buoyancy forces. That's why this has come into the equation. And here GB delta T is basically buoyant forces or buoyancy forces per unit mass. ठीक है, चलो. So Grosshoff's number तो we already know. Okay. Now next is, now how do we define DH? How do we define DH or this LC? LC again is characteristic length. Okay.
Sir.
So it is slightly different. Yes. Who is this?
Sir, Vijay.
Tell me.
Sir, in writing test series, I have found one question, sir.
Okay.
So they ask for the graph of beta versus temperature, sir. How it will be?
Okay. Beta versus
temperature. Okay. They have given this 1 by V into dV by dt.
They have given this equation and they are asking ki draw beta versus temperature. So look, what will happen? I am not very sure. I have not seen the graph, but anyway, I'll tell you two things may happen. What will happen? Look, when temperature is increasing, volume is increasing, so buoyancy forces may increase. Okay, but as temperature increases, density of this fluid decrease. Density of this fluid will decrease. Okay, because it as I told you, by if it is, for example, air is there, so P density is equals to RT. If temperature increases, density increases. So fluid will be less dense. So now the buoyancy forces this body will apply on the fluid will be less. So it can also decrease. Okay. So it can increase, it can decrease. So what were the options? Do you remember the options? Or they were just asking, I mean, there must be few options, right? Vijaya?
Yeah, they have given the 4 graphs, sir, actually. One was rectangular hyperbola.
Okay.
Hello.
Was there any
Set,
graph that was increasing or increasing and decreasing both?
it means the question was actually the test was closed, sir. The results will be announced tomorrow. I will send you tomorrow, sir. Otherwise,
Okay, your test series question. So you can send
yeah,
me
it
that
was
question once you get it. Okay. But it
okay.
can cause both. It can 1 second. Arey yaar. So it can do both. It can increase the buoyancy forces. It can decrease the buoyancy forces as well. Okay. So if you had similar kind of graph there, that could be the right answer. Okay.
Okay, sir.
Chalo. Now LC, how do you calculate LC? LC will be surface area upon perimeter. Surface area upon perimeter. So in vertical plate, LC is equals to L. LC is equals to L. Or L will be basically how much ever length of this plate is submerged in what? Submerged in the fluid. Okay. Inclined plate also LC is equals to L. But if it is horizontal plate, then it is area upon perimeter. Area upon perimeter is surface area upon perimeter. Okay. If it is vertical cylinder, then LC is equals to L. If it is a horizontal cylinder, then LC is equals to diameter. Okay. Sphere again, LC is equals to D. So this LC we are going to use to calculate Grashoff's number. Grashoff's number. Okay. Now the next, also we have, Nusselt number and Prandtl number also play a role in free convection. Look, Reynolds number is exclusively for forced convection, but Prandtl number and Nusselt number comes in free convection as well. Now, as we have talked about Reynolds number, Nusselt number we have defined, right? If you remember, we have defined Nusselt number in forced convection. 1 second. Okay. Nusselt number was some constant. Reynolds number 1 by 2, Prandtl number 1 by 3, something like this was there. So it was a function of Reynolds and Prandtl number. Okay. But in free convection, Nusselt number is a function of Grashoff's and Prandtl number. Grashoff's and Prandtl number. Okay. Next is Rayleigh number. So Rayleigh number is basically the product of these two. It is the product of these two. It is the product of Grashoff's number and Prandtl number. Okay. So Nusselt number, I can also write it like this. Is equals to function of Rayleigh number. Okay. And we can show it by using same thing like constant RAL Rayleigh number M. Now constant and M, they are, this C and M are, they are some constant. Now, if Rayleigh number is less than 10 to the power 9, if Rayleigh number is less than 10 to the power 9, then laminar flow, then it is a laminar flow. Okay. If this is again the critical number, and it is used to determine if it is laminar or turbulent. So if in the question they will say Grashoff's number or Rayleigh number, they both are correct answer. They both are correct answer. Okay. Now, Rayleigh number is less than 10 to the power 9. Rayleigh number, if it is less than 10 to the power 9 in free convection, then it is laminar flow. And here usually M values is 1 by 4. If Rayleigh number is greater than 10 to the power 9, then it is turbulent flow and M is equals to 1 by 3. M is equals to 1 by 3. Okay. And the last is Richardson number. It basically tells you that which phenomena is dominating, free convection or forced convection. There is a derivation for it. Of course, we do not need the derivation. So it is defined as Grashoff's number divided by Reynolds number ka square. If a surface is subjected to external flow, the problem involves both natural and forced convection. Okay, some fluid will be flowing because of natural convection, and some will be flowing from forced convection. The relative importance, which phenomena is dominating, free convection or forced convection will be told by Richardson number. So if Richardson number is less than 1, of course, Greshoff's number will be greater than Reynolds number square. Now this is telling you free convection. This is telling you forced convection. So in this case, natural convection is dominating. If it is less than 1, of course, then it is opposite. It is opposite. Okay. So here forced convection is dominating. And if it is equals to 1, then it is a mixed. Then it is a mixed. Matlab forced and free convection, they are of equal importance. They are of equal importance. Okay. ठीक है. Is it clear? Chalo, now we have 1 hour left. 1 hour left. And we have to, of course, do questions. We cannot leave without questions. And let's see how much what we have learned, what we have derived till now, how much is useful for us. Okay. Chalo, let's start with the question. An uninsulated air conditioning duct of rectangular cross section 1 meter into 10 to the power 5 meter. So you have a rectangular duct. Now this is your 1 meter. This is your 0.5 meter carrying air at 20 degree Celsius with a velocity of 100 meter per second. So T of air is equals to 20 degree Celsius, 20 degree Celsius. Okay, inside the duct. And its velocity is equals to 10 meter per second, V infinity. It is exposed to the ambient of 30 degrees. So हमारा T ambient कितना है? 30 degrees. Now effect of duct construction can be neglected. For air in the range of 20 to 30 degrees, this data is given. K is given 0.025 watt per meter Kelvin. Viscosity, and this is dynamic viscosity, 18 mu Pascal per second. That means, how can I write this? How can I write this? 18 into 10 to the power minus 6 Pascal second. Prandtl number is also given. Density is given 1.2 kg per meter cube. For laminar flow, Nusselt number is 3.4 for constant wall temperature conditions, and for turbulent flow it is. So you see they have given, if it is a laminar flow, we will come to that. Wait, we will come to that. If it is a common data question. If it is a laminar flow, then Nusselt number is constant 3.4. If it is turbulent flow, then Nusselt number is 0.023, Reynolds number 0.8, Prandtl number 0.33. So this is given in question. Now, what are they asking? The first thing they are asking is the Reynolds number for this flow is. So first of all, we need to find out. It is first question of this data. Reynolds number we need to find out. So can you find out Reynolds number out of this? Let me drink a sip of water. Okay, 4.446. That is actually correct. So, Reynolds number is very simple. By rho V D by mu. Rho we know, V infinity we know, mu we know. I need to find out DH. Okay, DH will be equals to 4 area of cross section upon perimeter, and I have already defined it for you, 2AB upon A plus B. So 2 into 1 into 0.5 upon 1.5. So it is 1 upon 1.5. It is 0.667 meter. Everything else is known to me. By density is how much? 1.2, mu is 18, and V infinity is 10. V infinity. Have you calculated it? Have you calculated it? Yes, yes, I can go back. Of course, I can go back. See, this is. Yes, that is also correct, Sean. Shruti and Sai, have you calculated this? Shruti, can we move ahead? Yeah, there is no, defined time for any question. Let me tell you this. There are sometimes 2 marks question that takes less time than sometimes 1 mark question. Like sometimes 1 mark question takes more time than 2 marks question. It depends on the question. Like this did not take you much time, but the next part will take you much more time. So there is no, but I would say if it is 1 mark question, then you can solve it in around 20 seconds, 20 to 25 seconds. If it is 2 mark question, then not more than 1 minute, not more than 1 minute. But again, sometimes that 2 mark question, you will be able to do it in 30 seconds. And then some other question, you can take 2 minutes because you have saved time in some other question. Okay. So it depends on the question. It varies from question to question. Like this did not take, it should not take, once you have read the question, it should not take more than 30 seconds to solve this question. Okay. So the Reynolds number we have found. Arey yaar, 1 second. Chalo. So Reynolds number is, we have calculated to be 4.44 into 10 to the power 5. Okay, Reynolds number we have gotten. Now they are asking heat transfer per meter length of the duct in watts. So length will be 1, and I need to find out heat transfer, which is equals to H A T S minus T naught minus T infinity. Okay. Now I need to find out H. I need to find out H. How do I find out H? Anyone? Nusselt number, of course. What is Nusselt number? Is equals to HLHD by K of fluid. Now this I know. This I know. If I know Nusselt number, I can calculate this. Now in order to see Nusselt number, I need to find out, is it laminar or turbulent? So can you tell me, is it laminar or turbulent flow? Is it laminar or turbulent? Turbulent, of course, because the condition critical Reynolds number is 2000 for laminar. Okay, and if it is greater than 4000, it is turbulent. So it is of course turbulent. It is much greater than 4000. Okay, chalo. So it is turbulent. So this will tell you as Reynolds number is greater than 4000, the flow is turbulent. Now I need to use turbulent formula. Nusselt number is equals to 0.023 Reynolds number 0.8 Prandtl number 0.33. 0.8 Prandtl number 0.33 is equals to H dH by KF. By Reynolds number I have calculated, Prandtl number is given in question, dH I know, KF is given in question, I can find out H. Tell me very quickly what is H. I am going to give you the values. These are the values. H Sahil has calculated 25.636. Very nice. That is actually correct. Everyone solve this question and tell me what is the answer. H. And then calculate Q, because we need to calculate Q. Yes, that is right. Very nice. So area, what is area? So area, yes. Length into perimeter, you can say, of course. What circular? D N L. This is not circular, no. This is rectangular. Yeah, hydraulic.
Means we are calculating Nusselt number based on the hydraulic, no sir, hydraulic diameter, no sir.
No, that is, yes, that is hydraulic only. Yes, that is hydraulic only. So that we have already calculated, no? DS2 we have calculated here.
Yeah, but the area also we need to calculate from the DH only, no sir.
No. That is what area? You see, this is what area? This is H. I am going to tell you this Q is equals to HA. What is this area? When you do remember the definition of Newton's law of cooling? Do you remember that definition? It is the area of heat transfer, area that is in contact with the fluid. Surface area. Yes, area exposed during convection. It is the area that is in contact with the fluid. So it is the surface area. So what will be this area? By you can say area into perimeter, of course. Perimeter is 2A plus B into L. वो perimeter into length you can say. Or 2AL plus 2BL, whatever you want to call. ठीक है?
Okay, sir.
Okay, sir. We always look, whenever we are going to use conduction formula minus Ka dt by dx या dt by dy, always will use area perpendicular to heat transfer. Whenever we are going to use this equation, we are going to use surface area there, the area that is exposed to the fluid, that is the area of heat transfer. Okay, not hydraulic. That we are using here, no? Nusselt number we have put, Reynolds number we have put hydraulic diameter here. That's why we are calculating Nusselt number.
Means we are converting the rectangular duct into the Nusselt number. A circular duct, no, sir, for calculating the Nusselt number.
Why we are not turning it into sphere?
Circular duct, sir. No, Nusselt number.
No, this
sir,
DSV.
I seen in some textbooks, sir. I forgot the name of the book. He calculated based on. he take the surface area of the cylinder, sir. That hypothetical cylinder coming from the DH.
Okay. Maybe they have used it, but did they take hydraulic or did they take surface area?
They take the surface area with DH into L, sir. Pi DH into L.
Acha, DH into L. Try to do that. How much you are getting? Try to do that.
Okay, sir.
I am very sure we have to use surface area. Probably this is one other way of doing it. I am not aware of it. Okay, just see if you multiply DH into L is basically not known to us anyway. Okay.
Area coming was 0.2 meter square, sir.
Area is
0.2 meter square.
okay.
Pi
Tell me
into
one more
DH.
time. What did they do? They multiply hydraulic diameter into what?
They take the height. They convert the rectangular section into the hypothetical cylinder by DH, sir.
ठीक.
DH.
And then
Then they calculate the Nusselt number from the DH, as well as they take the area as a cylindrical surface, sir. Pi DH into perimeter of that circular cross section into the length.
but
Instead
length
of take,
anyway you don't.
yeah, per meter was
pi
given,
DH. Okay. ठीक है.
yeah.
So I
That
am not very sure because we have not converted into length.
Okay.
Hmm.
The same what we take the rectangular perimeter into length, they have taken the hypothetical ones. Right?
Okay. Try to solve it till the end, then we will cross check the answer.
Okay.
So H you have gotten right 25.6188. How much Sahil calculated? Okay, 25.636. ठीक है, 63 whatever. ठीक है, watt per meter square Kelvin. So I know H now, and H I can put here. Area I can put here. This will be 3L. Okay, and L will be equal to 1. So I can put it here. AR is 30, T infinity is 20. So Q dot is 768 watts. Okay, we need to move a little fast because if we solve, yeah, area is 3L, yes. If you put A and B values, then you can take as 1. Yes, L you can take as 1, no? So 3L is right. No, this is surface area. What you are saying, we have to find out surface area. What is surface area? My surface area will be, what area is in contact with this? Look, this and this, so 2A, and this and this plus 2B, and then length. So it is basically 2A plus B perimeter into length. So this is 1.5 into 2, 3, 3L. Okay, chalo, let's move a little faster, because if we have to do at least, I don't know how many questions, but of course it is going to take more time. We cannot go with this speed. Chalo, theek hai, next question. For flow of fluid over a heated plate, the following fluid properties are known. Viscosity is given, mu is given, specific heat Cp is given, thermal conductivity K is given, K of fluid, hydrodynamic boundary layer thickness at a specified location on the plate is 1 millimeter. What is it? Delta H is equals to 1 millimeter. and I need to find out thermal boundary layer at the same thickness. Thermal boundary layer at the same thickness. So, do you remember the Prandtl gave you one relation? Prandtl gave you one relation. What was that relation? By thermal boundary layer by hydrodynamic boundary layer is equals to 1.026 Prandtl number minus 1 by 3. Minus 1 by 3. Yes, that is right. That is right. Okay. So Prandtl number you can calculate. Look, you know this. If you can calculate this, you can find out thermal boundary layer. So Prandtl number will be equal to mu Cp by K of fluid, right? Now mu is given this 0.001. Cp is 1, but this is in Pascal, this is in kilojoule. So it will be converted into 1000, and thermal conductivity is 1 watt. Okay, so it will be equal to 1. So can I say, and this is 1 millimeter is equals to, I can approximate this as 1 as well. Okay, 1 into Prandtl number is 1 minus 1 by 3. So it is, everything will turn out to be 1 millimeter. Okay, yes, 1 millimeter is the right answer. Yes, delta H is equals to delta T. That is right. Okay. Chalo. So 1 millimeter is the right answer. Let's move on. Let's move on. A coolant fluid at 30 degrees Celsius flows over a heated plate maintained at, what do we have? We have a heated plate. This heated plate is maintained at T of wall, let's say 100 degrees Celsius. And a coolant fluid is flowing over it. A coolant fluid is flowing over it. So T infinity is equals to 30 degrees Celsius. Boundary layer distribution at the given location on the plate. Boundary layer temperature distribution at a given location on the plate may be approximated as this. So temperature, how deep temperature is changing with Y? 30 plus 70 exponential minus Y, where Y is the distance normal to the plate. Okay, in this direction Y is changing. Thermal conductivity is 1 watt per meter square, watt per meter Kelvin. Local convective heat transfer coefficient I need to find. Out. Okay. So you remember the basic equation. At the surface. Q dot conduction will be equals to Q dot convection. So from here, I can write H is equals to minus K dt by dy at y is equals to 0 upon T wall minus T infinity. Do you remember this formula or not? Yes, minus K actually. Okay. Chalo. Now I need to find out dt by dy. So this is my T. dt by dy will be equal to 0 plus minus 70 e to the power minus y, right? Now dt by dy at y is equals to 0 is equals to minus 70 into e to the power minus 0. So e to the power 0 is 1. So it will be this. Okay. So I can write minus 1 into minus 70 upon 100 minus 30. So what is the answer? Can you tell me? What is the answer? B is the right answer. Very nice. Okay. It is 70 by 71 watt per meter square Kelvin. Watt per meter square Kelvin. Okay. Is it clear, everyone? Let's move on then. Shruti, Sai. Chalo. Next question. The ratio of laminar hydrodynamic boundary layer thickness to thermal boundary layer thickness of flows of two fluid P and Q are, so it is saying hydrodynamic and thermal for P is equals to 1 by 2, and hydrodynamic by thermal of Q will be equal to 2. Reynolds number based on the plate length for both. Now Reynolds number is same for both, 10 to the power 4. Prandtl number and Nusselt number for P is given by Prandtl number for P is equals to 1 by 8 and Nusselt number for P is 35. The Prandtl and Nusselt number for Q I need to find out. So by Prandtl number to dekho, it's very simple. Prandtl number to we know that, let's say Prandtl number for Q minus 1 by 3 is equals to hydrodynamic by thermal of Q. Why? Because we have 1 upon 1.026. This we approximately take as 1, just for a rough calculations. Okay, we take it as 1. So we do not need this. It is Prandtl number minus 1 by 3. Now this is given to me. This is equals to 2. This is equals to 2. So Prandtl number Q is equals to 2 to the power 3 to the power 3. Okay. Now, are we doing right? No. Yeah. There is a mistake. No. It is thermal by hydrodynamic. It is thermal by hydrodynamic. This was the actually relation. Okay. So this was the relation. So it is equals to 1 by 2. It is not 2. It is equals to 1 by 2. So Prandtl number now is equals to 1 by 2 minus 3, isn't it? And if I can replace this minus, I can write 2p is equals to 8. Okay? Is it clear? Okay. Now, what do you know about Nusselt number? Nusselt number for any, let's say Q is equals to some constant was there. Some constant was there, right? Reynolds number 1 by 2, Prandtl number 1 by 3. Okay. Now, if you remember the constants, it's well and good. If you don't remember, it is also okay. Why? Because I can do Nusselt number P. Otherwise, I can directly write constant. Reynolds number is given to me. Prandtl number I have calculated. I can directly calculate Q. If I don't remember constant, then let me divide it by this. Reynolds number of P 1 by 2. Prandtl number of P 1 by 3. Constant and constant will get cancelled. Nusselt number I know for P. Prandtl number I know for P. Reynolds number I know for P. Reynolds number for Q is also same. Prandtl number for Q I have calculated. So I can calculate Nusselt number for Q. How much is it? Can you tell me? 139.66. ठीक है, 139.66. So it is 140. It is 140. So what is the right answer? A is the right answer. Yes, A is the right answer. ठीक है? Is it clear, everyone? Shruti? And Sai, have you solved this? Sean? Shruti has said A. Okay. Chalo. Should we move on? Okay, chalo. Sean, chalo. Now next question. The temperature distribution within the thermal boundary layer over a heated isothermal flat plate is given by, this is your dimensionless temperature distribution that is given to me. Okay. TW have wall temperature, T infinity is ambient temperature or free steam temperature, and y is the distance normal, distance measured from the plate. The local Nusselt number based on the thermal boundary layer thickness is given by. Okay, so we have to find out local Nusselt number at a particular x. It will be equal to hx x by k of fluid, isn't it? Now I need to find out at a particular boundary layer thickness. It is based on the particular boundary layer thickness. Okay, now hx, what is hx? Look, if I can find out hx, I can put in this and I can calculate this. Okay, so hx will be equal to minus k dt by dy at y is equals to 0, t surface minus t infinity. Now temperature is given to me. I can find out dt by dy at y is equals to 0. I can find out or not. Can you find out dt by dy at y is equals to 0? Because temperature distribution is given to you. Yes or no? It's simple only, right? Yes, we can find out. So how can we find out? By ठीक है, let me do it here itself. I can find out dt. So it is I can dt by dy minus 0 is equals to 3 by 2 1 upon delta t infinity minus tw minus 1 by 2 3y square by delta t infinity minus tw. Okay, now let me take dt by dy at y is equals to 0. Okay, so what would it be? It will be equal to 3 by 2 1 upon delta t infinity minus delta tau, because this thing will go to 0. Y is there, it will go to 0. Now let me substitute this here. If I substitute this here, I will get minus k 3 by 2 1 upon delta t infinity minus t w, and ts, और ts को मैं ले देता हूं t wall. ठीक है, ts I write t wall minus t infinity. Now what can I do? I can swap this. I can swap this and I can take it as positive. I can swap this and I can cancel this. So hx, I have gotten 3 by 2 k upon delta t. Okay. So can I write? Look, what are they asking? They are asking the local Nusselt number based on thermal boundary layer thickness. So at a particular x, okay, let me take it ahead. Nusselt number at x is equals to h x by k of fluid. And just now I have find out hx is equals to 3 by 2 k upon thermal boundary layer. Okay. Yes, 1.5 is the right answer, right? Okay. So at a particular x, for example, this is your thermal boundary layer. Okay. So we are talking about at a particular x, what is the thermal boundary layer? Okay. So these relations are basically correlated to each other. Okay, they are correlated to each other. They are asking at a fixed delta t. They are asking at a fixed based on fixed delta t. So x will also be fixed. This delta t you will get at a fixed x only. Okay, so these are basically replaceable. X is equals to delta t. I can replace them. Okay, so let me write this 3 by 2 k by x. So I can write hx x by k is equals to 3 by 2 by this and this. And this is also equal to Nusselt number. So Nusselt number is equals to 1.5. So this is one way of doing it. This is one way of doing it. There is one more way that Vijaya said that you want, I mean, dimensionless, because it is a dimensionless temperature distribution. This is a dimensionless distribution. Okay. So Nusselt number is also given as hxx by k of fluid is equals to delta theta by delta y star, or sometimes we can show it by any other term, y star is equals to 0. Okay. From here also we can directly find out. Now there is a derivation, little small derivation behind it. Okay. If you want, we can, I have left some space, we can do it also. Okay. Chalo. So look. Do you want to do the derivation? Tell me very quickly, yes or no. Look, and I will, okay, let's do the derivation. It will not take much time. Let's take, anyway, it's 8:25. So I think we need to extend the class till 9 or probably a little late, but okay, let's do this. Okay, chalo. Local convective heat transfer coefficient. Local convective heat transfer coefficient. How can we give this? Hx is equals to minus k dt by dy at y is equals to 0 upon t wall minus t infinity. T wall minus t infinity. And Nusselt number is given by hx x by k of fluid. Okay. Chalo. Now let us assume some dimensionless parameters. Dimensionless parameters. What are these dimensionless parameters? X star is equals to x by L, y star is equals to y by L, and theta is equals to ts minus t upon ts minus t infinity. Okay. So these are some of my dimensionless parameters. Now, can I differentiate this with respect to y? Tell me. D theta by dy will be equal to what? D theta, it is equals to 1 upon ts minus t infinity. Okay, 1 second. ठीक है, चलो कोई बात नहीं. I think Sahil left. चलो, ts minus t infinity and 0 minus dt by dy, right? So can I can do what? I can d theta by dy is equals to minus dt by dy at y is equals to 0, at y is equals to 0, 1 upon ts minus t infinity. Okay, so yahan se I can find out minus dt by dy will be equal to, let me put it here, minus k d theta by dy, y is equals to 0. In fact, one minus will come here, into 1 upon, no, not 1 upon, just ts minus t infinity. Ts minus t infinity. That x square alpha. What is x square alpha? X is equals to x by L, huh? Yeah, it is x by L. It is a dimensionless x. X star. Okay, x star. ये y स्टार है। ओके चलो, और यहाँ पे वी हैव t वॉल को मैं s लिख लेता हूं t इंफिनिटी। ओके चलो, वी कैन कैंसिल दिस, वी कैन कैंसिल दिस, एंड इट विल बी k d थीटा बाई dy y is equals to 0. Y is equals to 0. Okay, did we miss anything? I think we have missed something. tw minus t theta x. Okay, ठीक है. Now this dy can be written as dy star into L is into dy, right? So I can write this k d theta dy star by L y is equals to 0. Y is equals to 0. So I can simplify it a little bit. Now I am talking about a particular x. Okay, so hx into this L, it's not a full length. We are talking about a local heat transfer coefficient. So this this L will be x by k is equals to d theta by dy star y is equals to 0, and this is also equal to Nusselt number. So this was the derivation that I think Sahil was saying. Okay, so we can solve it both ways. We can solve it both ways. Now we can simply derive this. Now we can simply derive this how? By Nusselt number is equals to d theta by dy y star is equals to 0. Y star is equals to 0. Okay. So now what we can do, this is my theta. This whole is my theta. So I have theta is equals to 3 by 2 y, one second, y by delta t minus 1 by 2 y by delta t a whole cube. Now again we need to apply this. Again we need to apply it. We are assuming what we assume there, that our this we are what we need to calculate is at a it based on this thermal boundary layer. Okay, so it will be at a particular length, right? Whatever the thermal boundary layer is there, if it is fixed, so this length is also fixed. Okay, so we can replace this by either L or X. Okay, so it will be equal to if I replace this, I can write theta. Let me write it here. Theta is equals to 3 by 2 y star minus 1 by 2 y star square or cube. I think cube. ठीक है. I have replaced xt by L. Okay, chalo. Now I can do d theta by dy star is equals to 3 by 2 minus 3 by 2 y star square. Now I need to calculate d theta by dy. Y star is equals to 0. It will be equal to 3 by 2, and it is also equal to Nusselt number. Nusselt number is equals to 1.5. Okay, so you can use, but this, if you know already this formula, then you can directly apply this. Otherwise we can also solve it normally like we did that. Okay, ठीक है, let's move on. ठीक है साई, is it okay? चलो चलो नेक्स्ट क्वेश्चन, थोड़ा जल्दी चलना पड़ेगा हमें, 9 बजे तक वी नीड टू फिनिश द क्लास. ठीक है, चलो नेक्स्ट क्वेश्चन. water enters a pipe. Okay, we have pipe here and water is entering. water का C specific heat ये है and mass flow rate is this is mass flow rate and temperature is 20 degrees Celsius. Temperature is 20 degrees Celsius. The pipe of the diameter 50 millimeter. So it is 50 millimeter. Okay, let's do one thing. This is a big question. Let us come back. Otherwise, we have just done a big question. Let us not. We will try this at the end of the session. Okay. Let us try to solve some small questions. Okay. So okay, this let's skip this. Let's do this one. Okay, we'll come back. Don't worry, we'll come back. Okay. Now this question: for laminar force convection over a flat plate, if the free steam velocity increased by a factor of 2, heat transfer coefficient. How heat transfer coefficient is going to vary? How heat transfer coefficient is going to vary? Okay. So it is telling me that Nusselt number is equals to HL by K is equals to some constant, Reynolds number 1 by, and it is about laminar flow. That's why I am using this formula. Okay. And Prandtl number 1 by 3. Okay. Now what is Reynolds number? Can you tell me what is Reynolds number? Rho V D by mu. Okay. Rho V D by mu. If I am taking D here, so let's take D here as well. Okay. Prandtl number is basically del upon del T. Okay. It's now what do we see here? It is equals to 1 by 2. Okay. So we see here that heat transfer coefficient is basically proportional to velocity, actually under root velocity, velocity power 1 by 2. Okay. So now they are saying average heat transfer coefficient I need to find out. So H2 by H1 is equals to under root V2 by V1. Now I have increased the free steam velocity by a factor of 2. It is free steam velocity. Okay. Reynolds number, free steam velocity. Now I have increased my free steam velocity 2 times of the initial velocity. Okay, so it is 2v infinity 1. This is v infinity 1. This will get cancelled. So H2 is equals to under root 2 times H1. So heat transfer coefficient is going to increase by under root 2 times. Rises with a factor of under root 2. Yes, very nice. Okay, so C is the right answer. Let's move on to the next question. A non-dimensional fluid temperature profile near the surface of a convectively cooled flat plate is given, where y is measured as perpendicular to the plate. Now A, B, C are arbitrary constant. A, B, C are arbitrary constant. T wall and T infinity we know. It is the wall temperature and ambient temperature. Thermal conductivity is K and wall flux is Q double dash. So it is basically watt per meter square. ठीक है ना? So the Nusselt number they are asking. So Nusselt number is given by Q double dash TW minus T infinity L by K. Okay. So they are asking Nusselt number. So how do I calculate Nusselt number? Its unit is basically watt per meter square. It is heat flux. Okay. So we know that heat by conduction will be equal to, at the wall will be equal to minus K. A is basically here. Okay. It is Q dot area K dt by dy at y is equals to 0. From here I can calculate my this. Okay. No, 1 second. This is wrong. It is here. Per unit area. Okay. So I can calculate this if I know this. And I can substitute in this equation and I can find out my Nusselt number. Okay. So dt by dy I need to calculate. Dt by dy 0 minus dt by dy is equals to 0 plus b by L plus c 2y by L. ठीक है, and everything multiplied by tw minus t infinity. ठीक है, yes, the sign that is right, b is the right answer. Okay, chalo, so minus dt by dy will be equal to, at y is equals to 0, will be equal to b by L tw minus t infinity, because it is already 0. This will also go to 0 as I put y is equals to 0. Okay, so if I substitute this here, so q double dash is equals to minus k, and dt by dy is minus b by L tw minus t infinity. So minus minus will be plus. Okay, now if I substitute it here, what? K b by L tw minus t infinity, okay, by tw minus t infinity into L by k. Okay, so this L will be cancelled by this k will be cancelled by this will be cancelled by this, Nusselt number will be equal to b. Okay, so this is my right answer.
Sir,
Yes.
whatever the non-dimensional temperature was there, no, sir, it directly hit the B answer, sir. Means it directly gives the B, sir, without doing all these things.
What? One second. What are you saying?
Dou theta by dou y was there, no, sir, that formula.
Achha, okay.
It
From that you
directly
can
gives,
directly solve it. Yeah. You can directly. Okay. Yeah. You can directly do that. Yes, that is right. Chalo. ठीक है. Let's move on to the next question. Water flows from a tube of diameter 25 millimeter at an average velocity. Okay, so water is flowing through a tube, diameter is 25, average velocity v average is equals to 1 meter per second. Okay, properties are given. Kya given hai? Density is given, dynamic viscosity is given, k is given, and Prandtl number is also given. Now Nusselt number is given. The convective heat transfer coefficient I need to find out. Convective heat transfer coefficient I need to find out. Very simple. H d by k of fluid is equals to 0.023, Reynolds number 0.8, Prandtl number 0.4. So look, I know d, I know kf, I know Prandtl number. If I will be able to determine Reynolds number, it's very easy for me, right? So calculate Reynolds number. Rho v average d upon mu. I know everything. Rho I know, v average I know, d I know, mu I know. Calculate very quickly. Tell me what is Reynolds number. What is Reynolds number?
Sir, mu was either
Hello.
7.2. Mu, sir, mu value 7.25 into 10 power 4 or minus 10 power 4, sir.
It is 10 to the power. It should be, I think it should be -4.
Yeah.
It should be -4. Yeah, these values are very small. What is Reynolds number? Yes. Sorry, Shruti, that mu is -4, not 4. Okay, that is -4. Okay, so you just multiply it by 10 to the power 4. Actually, no, multiply by 10 to the power 8 because you have already divided that. Yes. So this is 34,482.75. It is laminar or turbulent. Is it laminar or turbulent? Yes, it is turbulent because it is greater than 4,000. Okay. So the relationship is given to me. For turbulent, the relationship is given to me. As Reynolds number is greater than 4,000, it is turbulent. Okay. So it is Nusselt number. Now I know everything. Tell me what is H. What is H? I know Reynolds number, I know Prandtl number, I know D, I know KF. So I will be able to easily calculate this. Quickly. 4613 is absolutely right. 4613.66 watt per meter square Kelvin is absolutely right. Very good. Chalo, let's move on to the next question. It's very easy, right? Tell me what is the answer. Biot number, Kirchhoff's number, Prandtl number, Reynolds number. A, B, C, D. What is the right answer? Yes. A is the right answer. Anyone who has any doubt in this? Sean, Shruti has already answered. Sean, Sahil, I think, has gone. He had to do something. He texted. Chalo. Why B? Vijaya? A, no. B says, okay, ठीक है. A4 is right. B, C. No. A is the right answer, right? B ko you cannot. Here we have A, B, C, D. Okay. Vijaya, is it A or B? Yes, A is right. Sean, is it clear? Chalo, Sean said also clear. A is the right answer. Let's move on. In a laminar flow, when Prandtl number is 0.7 over a heated plate, del and del T denotes respectively. This is hydrodynamic and this is thermal. The hydrodynamic and thermal bound. Then tell me very quickly what is the right answer. Prandtl number is given by what? C is the right answer. Very nice. It is given by momentum diffusivity upon thermal diffusivity. Okay. And if it is less than, if it is 0.7, means that hydrodynamic boundary layer is less than, or hydrodynamic boundary layer is equals to 0.7 times of thermal boundary layer. That means it is less than delta T. So C is the right answer. Okay. You can use that, of course. Look, again, you have to do the same. It's the same thing. Look, Prandtl number -1/3, 1 upon 1.02. You can use the whole equation. Delta H, delta T, delta H, sorry. delta T, delta H. Okay, let us assume this as 1. Then parental number minus 1 by 3 is equals to thermal upon this. Write this 0.7 minus 1 by 3. I don't know how much it is coming. Tell me how much is it coming? How much is this coming? 1.126. So now what is it telling you? It is telling you that thermal boundary layer is 1.126 times of hydrodynamic boundary layer. So thermal layer is basically greater than hydrodynamic boundary. Same answer, no? Okay. Chalo. Next question. For a flow of viscous fluid over a flat plate, if the fluid temperature is same as the plate temperature, the thermal boundary layer is, tell me, fluid temperature and, yes, very nice, fluid temperature and plate temperature, they are at same temperature, or temperature thermal boundary layer forms because of the temperature difference. If there is no temperature difference, there will not be any thermal boundary layer. Okay, very nice, very nice. Chalo, next question. For flow through a pipe of radius r, the velocity and the temperature distribution are as follows. Velocity is given, temperature distribution is given, and mean temperature is given, where um being the mean velocity. They are asking tm. So I need to find out tm is equals to 2 umr square 0 to r c1 into tx is c2 1 minus r by r whole cube r dr. No hydrodynamic will form, no, because it forms because of the velocity. That will always form. That, look, if the velocity, if it is moving, if any velocity is there, they did not say tell about velocity. If it is moving at a velocity, then here velocity is 0, and away from this velocity is u infinite. So of course it will be formed. Of course that there will be a velocity gradient, and of course this will form like this. Okay, because if velocity is 0, then it will not form. If the fluid is not moving, then it will not form. If the fluid is moving with a velocity, then of course at the surface velocity will be 0. Away from the surface, velocity will have a finite value. So if velocity gradient are there, then it will actually form hydrodynamic boundary layer. Okay, chalo. Okay, we have to do this. So I have put u1 like this, and t by this, and rdr. Now I need to integrate by, I can say, c1 c2 upon umr square 0 say r 1 minus, in fact r minus r4 upon r cube dr. Okay, now look, u is varying in r and x direction, but it is still a constant. It is still a constant. Okay, so u at any r or any x is basically a constant. So it is also equal to u is equals to, at any r or any x, it is a constant. So basically it is also is equals to a constant, because will also be at a r and a x. Okay, so it will also be constant. This will get cancelled. Okay, c1 and now c2 upon r square r square by 2 minus 3 minus 4r cube, sorry, 4r cube 4r cube. No, we are integrating, no, r5 by 5 r cube 0 to r. Okay, So if I put r here, 2c2 r square, this is r square by 2 minus r5 by 5r cube. So here also we have square. Okay. So Tm will be equal to 2c2 upon r square, r square by 2 minus r square by 5. So it will be 10 and 5r square minus 2r square, right? 2c2r square is equals to 5r square minus 3r square into 3r square by 10. I square will get cancelled, and it will be 3 to 6, 0.6 C2. 0.6 C2. So my T mean is equals to 0.6 C2. Okay. Is it clear? So C is the answer. Let's move on. Let's move on. Chalo. Shruti, is it clear? Why, tell me? We have actually not applied any concept here. It is simple mathematics. T mean I need to find out, and T mean is given in the form of U and T. I have just put the values and integrated it. That's all. Okay, okay, ठीक है, do it, do it. चलो चलो ठीक है, let's move on. Let's move on. Next question. A fluid whose Prandtl number is 1 at 500 Kelvin flows over a plate of 1.5 meter length maintained at 300 Kelvin. Okay, so here plate is maintained at 300 Kelvin. Yeah, flat plate is maintained at 300 Kelvin. So wall is 300. This is T infinity. Prandtl number is there. Length is given. Velocity of the fluid is, so this is V infinity or U infinity. Assuming kinematic viscosity, thermal boundary layer thickness is 0.5 meter from the leading edge. So I need to find out thermal boundary layer at X is equals to 0.5 meter. 0.5 meter I need to find out. It's very simple. Look, they have given Prandtl number. I have a hydrodynamic boundary layer at X is equals to 0.5 is equals to Prandtl number minus 1 by 3. Minus 1 by 3. Isn't it? I can also take 1.10 this, but it is okay. Even if I don't take it, it's fine. Okay. But still, I would suggest you that in numerical answer type, it is because this is the exact equation actually. This is the exact equation. So in numerical answer type, I would suggest that you take this value, because in objective type, you have they give you the options, so you can choose the closest option. But because it is numerical answer type, so it's better that you get as close value to the answer to as possible. Okay. Chalo. Prandtl number is given as 1. Prandtl number is given as 1, so it will be equal to 0.5 upon dh x 0.5 is equals to 1 upon 1.026, 1 minus 1 by 3. So it is basically 1 upon 1.026. Now the point is how to find this 0.5. X is equals to 0.5. This is the question. So can you tell me, do you remember any relation of this? 6. What is that? 6.123. What is that? Thermal boundary layer. Thermal boundary layer could be. I'm not sure. Okay. So what is this relationship? Do you remember? It is Blasius equation gave this relation. Blasius actually gave this relation. Okay. So can you find out Reynolds number at x, which is rho u infinity x by mu, or u infinity x by nu, because kinematic viscosity is given. So u infinity is 10, it is 0.5, and it is 30 into 10 to the power minus 6. 16666.67. Okay, Sahil got 16 extra. Sahil got 16. Okay, so I think it is 1666666. Yes, 0.67. Yes. Okay. So that is your Reynolds number. Now you can substitute it here. 5 into 0.5 upon under root 16666.67. I don't know how much you will get. How much are you getting? 6.124 millimeter. Okay, ठीक है. 6.124 millimeter. Now you can substitute here. By it is x 0.5 upon 6.124 millimeter. So now you can find out thermal boundary layer at this point. How much is it? Look how much difference came, because you took one, right? You took one here, but I took 1 upon 1.026. So there is slight difference. So I would suggest whenever you solve a numerical answer type question, go for the exact equation. But if it is option, like you have options, then you can, without even, you can take it as 1 and you can solve it and mark the closest answer. So it is 5.968 millimeter. 5.968 millimeter. ठीक है, very nice. ठीक है, चलो, let us move on to the next question. It is based on free convection. Our thin vertical flat plate of height L, we have a plate whose height is L and infinite width. So this width is infinite, okay? The perpendicular to the plane of figure is losing heat to the surrounding by natural convection. It is losing heat by natural convection. The temperature of the plate and the surrounding and the properties are constant. The relationship between average Nusselt and Rayleigh number is given. Okay, Nusselt number is equals to K Rayleigh number 1 by 4. 1 by 4 is given. Length scales for Nusselt and Rayleigh number are the height of the plate. Okay, so they are saying when you calculate Grashoff's number or Rayleigh number, your LC will be length. Okay, if the height, now I am increasing the height to 16L. Okay, original height is L. Now I am increasing it to 16L, keeping all other parameters constant. Calculate H1 by H2. H1 is what? Heat transfer coefficient. ठीक है. Can I say it is HL by K of fluid is equals to K Grashoff's number into Prandtl number 1 by 4, right? So Grashoff's number, can I write G beta L cube delta T upon nu square into Prandtl number 1 by 4. Now, can I say that H into L is proportional to L 3 by 4? Yes. So H is proportional to L 3 by 4 minus 1. So L 3 minus 4 minus 1 by 4. H is proportional to 1 upon L 1 by 4. Okay. So can I say H1 by H2 is equals to L2 by L1 1 by 4? Yes, that is right. Sahil is correct. Okay. Now L2 is what? L2 is 16L. L1 is what? L. 1 by 4. L and L will get cancelled. And H1 by H2 is equals to 2. So the answer is 2. Okay. Now I have, this was the last question, I think. Yeah, this is the last question. Okay. Now this one question is left. Actually, it is not, very, it is a good question, but it's easy also. Like if you try to do it, just remember you have to integrate. Okay. It is given for a particular X and you have to integrate. So we can do this. There's no problem, but it's not very difficult. If you have any doubt, you can just tell me and I can share the solution of it. Or do you want to do it? Just tell me. If you want to do it, then we can do it. Like it may take, I don't know, another 5-7 minutes. Otherwise, you can also try it yourself. Okay, they both are saying do it now. Okay, ठीक है, चलो, we will do it. So what it is saying water is there. Water is there. It is entering into a pipe. This is the mass fluid and the temperature is 20 degree Celsius. Okay, so it is T infinity. Water temperature is T infinity. The pipe diameter is this and length is this, is subjected to a wall heat flux. You are giving heat is equals to कितना है ये 2500 watt per meter square, x watt per meter square. So that means it is not constant, it is changing with the x direction, changing in x direction. Okay, where x is in meters and it is direction of flow. X is equals to 0 here, x is equals to L here. The bulk mean temperature of the water leaving the pipe. Bulk mean temperature I need to find out. Bulk mean temperature that is leaving the pipe. Okay, so T bulk or T mean I need to find out. T mean I need to find out. So you tell me one thing. By it is heat that I am giving is changing with x. It is changing with x. So let me take a small area at a distance x of thickness dx, of thickness dx. So that small heat that you are going to give, small heat, small amount of heat that you are going to give will be equal to q dot into area, okay, into that small area dA, into dA, right? Now what will be the total area if I need to integrate this area from 0 to L, 0 to L, that will be the whole area. Chalo. Now what is Q double dash? Q double dash is 2500 x, okay, into area. Into area is what? Small area, pi d into thickness dx. Okay, thickness dx. Now we can integrate this from 0 to L. 0 to L we can do that. Okay, so it will be equal to 25. Let me take out 2500 pi, diameter is also same, 0 to L x dx, x dx. So can you calculate this for me? Pi d x square by 2, 0 to L. Length is also given 3 meters. Length is also given. So can you find out what is the total heat transfer? $2,500 into pi, diameter is 0.05 meter, L square is 3 square by 2, 3 square by 2. Okay, it is 1767.14. So this is the mean temperature. So when water is flowing in this, I am transferring heat. This, let's say the inside temperature is Ti and outside temperature will be T exit. Outside temperature will be T exit. Okay. And the mean temperature will be what I have calculated. Okay. What I need to calculate. Bulk mean temperature I need to calculate. Okay. So whatever heat I am giving, it is absorbed by the water. Okay, so this total heat that I am giving, when it is absorbed by the water, yes, that is right, Sahil is correct. Okay, so it is absorbed by the water and water energy will increase, mcp T out minus T in. Now inlet temperature I know, m dot I know, and C also I know. I need to find out what is my T naught. What is my T naught? So Sahil has calculated 62.255 and Vijaya has calculated 62. ठीक है, 62.255 is correct. So T naught or 62 is already given. 62 is the correct answer. Sean and Shruti, is it okay? Yes, Shruti. Chalo, 62.27 is also correct. Answer is B. Now it is common data question. So it was the A part of it. What is the B part? This is the B part. Okay. Now we are giving fixed heat flusk. Heat flusk is fixed. And convective heat transfer coefficient at the pipe outlet is 1000. The temperature in degrees Celsius at the inner surface of the pipe at the outlet. So if you see this is the pipe. Let's say this is the cross section of the pipe. Okay, it is the cross section of the pipe. Now they are asking water temperature is what we need to calculate first. But they look, this is water temperature. Okay, but this pipe will be at a certain other temperature and the heat will be transferred by convection. So they are asking this wall temperature or pipe temperature. I need to find out. I need to find out this wall temperature. Okay. So again, I'll do the same thing. What will I do? Now this heat transfer is fixed. It does not depend on X. Okay. So the total heat transfer will be 5000 into surface area. Whatever area you are, because whatever you are giving, it is absorbed by, you are giving it from the outside of the body, right? So into surface area. So you can find out total Q. Right? And this heat is absorbed by, okay, let's see. This heat is absorbed by water. So it will be same m dot Cp T out minus T in is equals to 5000 into surface area is what? Pi dl. I know D, I know L, I know m dot, I know Cp. I can find out the bulk mean temperature of water. Bulk mean temperature, but it is not what they are asking. They are asking, tell me the pipe temperature. So tell me what is T naught? What is the water temperature at outlet? Bulk mean temperature. Are you doing it? Yes or no? Chalo, ठीक है. Do it very quickly. Seventy-six point three three degrees Celsius. Now see, at the outlet here, at this point, water temperature here at the water temperature is at bulk mean temperature of water is T naught, and wall temperature will be something Now from the wall, heat is transferred by convection. Okay, so Q dot convection will be equal to H, this heat, whatever heat is transferred, is it is per unit area. Okay, Q double dash. So Q double dash is equals to H T pipe minus T naught. It is the inlet temperature. When the fluid is entering, here we have other temperature. Here we have outlet temperature. So they are asking calculate the bulk mean temperature at the outlet. जो पहला जो उन्होंने पूछा था, the last one. The fluid will be entering at certain temperature, right? That is Ti. But it is absorbing heat what I am giving. So that will be T out. T out could be different than T bulk temperature. Okay. I hope you remember that graph that I draw there. Okay, so this is T mean, this is T inlet, this is wall temperature, and this is your T out. 8.36. What is 8.36? Okay, look, this is your 5,000, this is your 1,000. Temperature of pipe I need to calculate, and T out I have calculated. For water, this is for water. This is for pipe. Okay, so temperature of pipe is 81.36 degrees Celsius, which is correct. So this is correct. Okay. So this marks our ending of convection heat transfer as well. And now we have almost done everything that we wanted to. So let us review the syllabus one more time. Let us take 10 more minutes before we finish this. Okay. So are you comfortable in modes of heat transfer? The simple form, okay, conduction, convection, Fourier's law, convection, Newton's law of cooling, and radiation, Stephen Boltzmann's law. Are you comfortable in that? Okay, then one-dimensional heat conduction, one-dimensional. So Fourier's law is one-dimensional only that we talked about. Okay, so all my equations, what equations? Q dot is equals to Ka T1 minus T2 by L. Q dot is equals to H A T1 T surface minus T. These are all one-dimensional equations. Okay. Resistance concept, of course, we are aware of that. Okay. Resistance in what? In plane wall, in cylinders, hollow cylinders, and in spheres. Okay. And electrical analogy also we know. Okay. Heat transfer through fins. Are we comfortable in this? We have three cases in this. Three cases: insulated tip, uninsulated tip, and infinitely long. Infinitely long. Okay, we will talk about that later. Sai, give me a call. I'll tell you. Actually, there is not much difference. Some countries follow MS, some countries follow MSc, some countries actually no one follows MTech. There is nothing called MTech anywhere outside. Okay, some follow M engineering. Very few follow M engineering, but MSc is actually equivalent to your MTech outside. So if you do, for example, mechanical engineering, there will be MSc in mechanical engineering, okay, or MS in mechanical engineering, okay. So there is not big difference in this actually, but it's that it is little science focused syllabus there, okay, but it is equivalent to your MTech. Let's focus on this for some time. Okay, unsteady flow, are we comfortable? Lumped parameter and Hassler chart. This is what we have done. Are you comfortable? Just be with me for some time. If we are together for this long, let's wait for some time, okay? Thermal boundary layer, dimensionless parameters in free and forced convection. heat transfer correlations for flow over flat plate. This is external flows and this is internal flows. Okay, so we have done this, right? This is the official syllabus. I have not cut down anything in this, or I have not added anything in this. It is same. So are you comfortable in this? Okay. Effect of turbulence, still we have not seen. Then heat exchanger performance, LMTD and NTU method. We have done this, right? Yes, of course you need practice. This is the very first time. You have to do it at least 4 time revision and practice so many questions before you go for exam. Okay. So LMTD and NTU method, are we okay with that? LMTD and NTU method? Okay. Radiative heat transfer, Stephen Boltzmann's law, Wien's displacement law, black and gray surfaces, view factor, and radiation network analysis. So this is our whole syllabus of heat and mass transfer. Of course, not everything that we have covered is in this. Okay, we have covered much more than this, but it is a broad terms. In broad terms, this is the syllabus. So we have almost covered everything. Effect of turbulence is not very, like important, but still there are some, relations. But of course, you don't need these relations. Okay, this is for laminar flow. This is for turbulent flow. Okay, so you can follow this. Of course, you don't need this. If it is a turbulent flow question, the relationship will be given to you in question. You just need to know these terms. When it is, what is the critical Reynolds number? Okay. Also, when we talk about hydrodynamic boundary layer, in laminar flow, it is parabolic. In turbulent flow, because it is much more like there is rapid intermixing. There is rapid intermixing. Here it is linear, here it is linear, and then it is increased like this. So it is something like this, not parabolic. Linear and then slightly parabolic. It is like this for turbulent. It is because of rapid mixing. So shear stresses are not very significant. Turbulent happens at very high velocity, right? When you increase velocity, then the flow will turn from laminar to turbulent. So turbulent have rapid intermixing, and even shear stresses are not very significant. Okay, so therefore it reaches to higher velocities. You see, it is going to reach higher velocities much faster. You see, here it is very low, but it has reached to higher velocities much faster because shear stresses are not very significant. Okay, so first of all, in turbulent we have little linear profile and then parabolic. Okay. So these are some relationships again for laminar and turbulent, Nusselt number, Prandtl number, and all. And it is for internal flow. It is for again the same thing will happen. Again the same thing will happen. What? It will go linear. It will go slightly linear first, and very rapidly velocity is going to increase like this, and then it will be like this, and then it will be like this. It is a turbulent flow. Again, because shear stresses are not very significant. Turbulent. Okay, so you reach higher velocities much faster. You see, much faster you reach higher velocities. Okay, again, these are some relationships. Here we have 4.36 and 3.36 for laminar flow, and this is for Nusselt number. Okay, again, you don't need to remember all this. These relationships you don't need to remember. Okay, chalo. Boiling and condensation, I am not covering because never they have asked any question on that. It is a ESC part. If you see any question, if I may have missed anything, if you see any question, it is a theoretical part anyway. Okay. So if you want to give it a read, it will not take more than half an hour to read everything and to have a brief idea. So if you see any question, let me know. I'll share the PPTs for boiling and condensation. Not many slides, not much, there's no derivation or any such thing. There is a graph that you need to understand. Okay. And nucleate boiling and all that thing. So okay, ठीक है, I'll share. ठीक है, so I'll share it tomorrow, and just remind me tomorrow, and now start practicing more and more questions. They have asked about nucleate boiling. Okay, if they have asked, ठीक है, I'll share it. It's just theory. Give it a read. Ki what is, and I have written it very beautifully. Okay, I have written it very, like point by point. I have written it. So just anyway, if I am going to teach you that, I am going to read it from the slide. Okay, I'm going to read it from the slide anyway, so there is no point. But whatever needed to be covered, I have covered that. Okay, I'll share that. I have not seen that question. I probably have missed it, but it's okay. No problem. There is nothing much there. Just reading part is there. Okay. Chalo to फिर let's say tata bye bye now, and I hope that we will meet again sometime. Let me know. I don't know if we will have any classes again, because if I have, I'll have it for the next batch. But whenever you see your results, let me know what is your rank and all, and if what we have covered helped you or not. Okay. I hope it helped you. I hope that you are much more comfortable than than you were earlier in heat and mass transfer. Okay. It's a very easy subject. Very easy subject. Okay. Chalo. The most difficult part is actually convection, but it is not very important for us anyway. Okay. Chalo. So thank you so much for this, for being with me, and let me know when you see your result, or you can, if you have any doubt, anyway you can ask me anytime. Okay. So if you have any doubt, ask me anytime. Otherwise, let me know once you get your results. I really would be very happy to know. Okay. Chalo. Tata, bye bye. See you soon. Bye bye. Thank you.